Hi, my name is Elias Castegren, and this video presents the work on the object calculus OOlong, which I developed together with Tobias Wrigstad at Uppsala University. It was first presented at SAC 2018, but this video is for an extended version, scheduled to appear in the winter issue of ACR 2018. As researchers, we work with understanding reality. Ultimately, we want our research to have a real-world effect and somehow make the world a better place. Unfortunately, reality can be quite complicated, and trying to understand every single detail at the same time can make research quite unwieldy. So instead, what we tend to do is to build models of reality, where we can abstract away some of the details that we aren't interested in, and perhaps make some simplifying assumptions. For programming language researchers, reality comes in the form of programming languages, and the complicated details include the underlying hardware and garbage collection. So typically, we use models here as well. Historically, at least for object-oriented languages, most of these models have been based on Java, for example featherweight, classic, concurrent, lightweight, middleweight, and welterweight Java. The contribution of this work is another such core object calculus called OOlong. It models what we feel are the most important features of object-oriented languages, such as aliasing and subtyping, and with ubiquity of multicore hardware today, we also include concurrency in the calculus. The most important design goal of OOlong, however, is that it should be simple to reuse and extend. OOlong in itself does not really have any interesting properties, but it aims to act as a starting point for researchers who want to study object-oriented programming. Probably the biggest difference to the calculi we saw before is that OOlong does not try to model Java in particular, but object-oriented languages in general, meaning that we do not tie the language's features to Java's design. But before we go into the specifics, we should ask ourselves the question, if there are already so many object calculi, do we really need another one? Well, it turns out, if we look at the features of the calculi presented before, they actually aim to model slightly different things and have different focuses. For example, featherweight Java does not even model mutable state. Some of the calculi are based on expressions, others on statements, or both. Classic Java models both classes and interfaces, middleweight and welterweight Java model both the heap and the stack, and so on. Looking at OOlong, we see that it's aiming for another point in the design space. The most notable difference is that it doesn't model class inheritance at all. Instead, it uses interfaces exclusively for subtyping. It comes with concurrency and synchronization out of the box, and the semantics have been fully mechanized in Coq, providing a rigorous theoretical foundation. Inspired by lightweight and welterweight Java, we also make the LaTeX sources simple to extend and reuse by providing a formulation of the rules using the semantics tool OT. This is an example OOlong program with added support for integers. Even though OOlong does not aim to model Java, a Java programmer should feel comfortable reading OOlong source code. To the left we see classes and interfaces, and to the right an example of using Finnish async style concurrency together with lock-based synchronization. We also provide a prototype interpreter written in OCaml for automatically type checking and running OOlong programs. It can be used by a researcher who is more geared towards engineering than developing models on paper. The source code for the interpreter, the Coq mechanization, and the OT rules are all publicly available on GitHub, and so are easy to pick up and start using for other researchers. Thank you for listening to this presentation. If you would like to know more, you can find the paper in the winter issue of ACR 2018.